Hey, here's your assignment number 4 being done by me, your physics teacher. So, we got here, Robin. I wonder if that's like Batman and Robin. Roller skating down a marked sidewalk was observed at the following positions at the times listed below. Alright, so at time 0, well, first let's see, this doesn't have any scaling on it, this graph, so let me just see. Going from 0 to 10, so 1, 2, 3, 4, 5, 6, 7, 8. I guess maybe I'll scale this by, I could add a little bit to the graph, or I could scale this by 2's. What do you think? How about if we go by 2? So 2, 4, 6, 8, 10. I'm going to do that. If you scaled it by 1's, that's fine. You just had to go off the graph a little bit, off grid. So how about the position? I'm going up to 30, so I always want to start at 0. So let's see how many boxes I have. 1, 2, 3, 4, 5, 6, 7, 8. If I went by 4's, then that would get me up to 32. Now, whatever you do here, so long as you can fit all the data on your graph, it's fine. But what you can't do is, you can't say, okay, my first one is 10, so I'll make that 10, and then the next one's 12, make that 12, and then this one is... whatever you decide your spacing is, it has to be the same for every box. It has to go up by the same amount for both axes. Every once in a while, I get students who are a little confused about that. So that spacing has to be consistent. And then 32 up here at the top. All right, let's plot these. So at time 0, he, she, Robin's kind of a gender-neutral name, so could be he, she, they. So 0, time, and position 10 meters. Time 1, position 12 meters. So time 1, that's halfway here. Position 12 meters. Time 2, position 14 meters. Time 5, position 20. Time 8, position 26. And time 10, position 30. And that is perfectly straight line. And I don't know, maybe you notice that what's happening here is every second that goes by, we're going up by 2. 1 more second, up by 2. Ooh, 3 more seconds, so I guess that would have to go up by 6, right? If we're going up by 2 every second. 3 more seconds, up by 6. 2 seconds, up by 4. All right, so we did that. Explain how you can use the graph to determine how far he... Oh, there you go. It's a he, I guess. Explain how you can use the graph to determine how far he was from the origin at time 6. Well, I just look at the graph here. At time 6, looks like it would be 22. Just find point, which is the position value at time equals 6 seconds. And it looks like it's 22 meters, which would make sense. 2 higher than that. All right. I think the point of that is, like, if you have a graph, you can always look at the graph and find points and do that. Write a mathematical model that describes a skater's motion. That means write the equation for this line. So if you read this and you were like, what the heck does that mean? Can you please pause the video and just go ahead and try to write the equation for this line? And before you pause, not like y equals mx plus b, but like the stuff that actually is going on here. So you can think y equals mx plus b. That's fine. But here, the y is called position, or x, because we're thinking about moving back and forth on a number line, like an x-axis. So x is equal to the slope of this line, which is, we just talked about it, it goes up 2 meters every 1 second, 2 meters per second. that's the slope. It needs to have these units. That's not optional. Times, so that's like my y equals mx time plus b, right? So this is my, from your notes, position is equal to velocity times time plus initial position. And when you write one of these in an actual situation, this is going to stay x, and this is going to stay a t, but these are going to be replaced with whatever the velocity and the starting position are for your particular context. All right, so that is what that should look like with the units, please. What was his constant? His speed constant? Sorry, that's backwards. Typo. What was his constant speed over the entire interval? How do you know? It's 2 meters per second. Slope of position versus time. It's the slope of that. Right? That's all. All right, what's next? Number 2. In a second trial, the timer started her watch a bit sooner, and the following data were obtained. So, time 0. Let's see, what are we going from? Up to 34 now. I think I'm going to still scale by 4s, and I'll just be like a little whisker above by the time I get to that last position. And same thing here, 2, 4, 6, 8, 10. If you scaled by 1s and just made a couple extra things over there, that's fine. All right, so at time 0, we are now at position 4. At time 2, we're at 10. Time 4, we are at position 16. Time 6, we are at 22. Time 8, we are at 28. And time 10, we're at 34, which is going to be a little off my graph. All right, plot. How far from the origin was the skater at time 5? It's like at time 5, that's right in between here. Now that's a little tricky to read from the graph. If we look at what the slope is here, I don't think this is cheating. It looks like we're going up now in 2 seconds. We went up by 6 here, so it looks like my slope of this is 3 meters every second. So how far from the origin was the skater at time 5? I'm thinking that that's 19, right? Because that's 3 above this, 3 below that. So you could read that from the graph, although you might have a hard time knowing that it was exactly 19 on that graph, unless you made a bigger, more accurate graph than my little sketch here. So read from graph or examine the data for the pattern. And when you examine the data for the pattern, what you're really doing is checking out what the slope is, right? So either one of those, it's 19. What's the skater's speed constant? I don't like that. Why did that happen again? Constant speed. What's the skater's constant speed? It's the slope. Oh, was the speed? Sorry, is that what the other one said too? Was the speed constant? Sorry, that's what it said there too. Was the speed constant? So that's fine. Sorry about that. Yes, I'll answer the question right. It was 3 meters per second. In the first trial, the skater was further along at 2 seconds. In the first trial, the skater was at 14 meters. at 2 seconds. Does this mean that he was going faster? No. The position at time 2 seconds in trial 1 was greater, but the velocity was less, right? Velocity in this one was only 2 meters per second. So what would that look like if they were like going off at the same time? It would look like the skater, if they're going like this way, here's trial 1, this skater is, trial 1, this skater's ahead, and trial 2 behind but going faster. So the one in trial 2 would be catching up to and eventually passing. We could even look at them side by side here and see like when does that passing happen. So where are they at time 2? 10 and 14 at time 5. We don't have the same ones, but at time 8 you can see that the second one has now passed, right? So how would you find exactly that intersection? Well, you could, instead of graphing them on two different graphs, you could graph them on the same one, right, and find where those two lines cross. Or if you wrote the equations for both of them, you could do a little bit of math and figure out where those two equations intersect, or what the solution to that system is. That's a thing you know how to do from algebra class. Okay, here we go. We got a third trial. Plot the position versus time. Now I got times from 0 to 16. Definitely got to scale by 2s now. And positions going up to 8. So that's how many I have here, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay. At time 0, we're at position 0. At time 2, we're at position 2. At time 4, I'm at position 4. Time 6, I'm at position 4. So there's two different times, but at the same position. So that's like a little bit of not going anywhere, right? Being constant position. Time 8, we have position 3. Time 10, position 2. Time 12, position 2 again, staying at the same place. And time 14, up to position 5, and then 16. Okay? So it looks like I got a little bit of constant velocity in the positive direction, and then a little bit of zero velocity. The slope of that is 0. And then a little bit of moving in the negative direction with a constant velocity. Looks like the slope of that would be -1. Slope of that is 2. Slope of this is 0. Staying still again for a second. And then here, looks like this has a slope of +3, so moving in the forward direction from 2 up to 8 over the course of 4 seconds. Sorry. Ooh, I told those slopes I said were wrong because this is 2 seconds per box. So there's my plot. What's happening from 4 to 6? Staying still. How do you know? Position remains the same or constant. What do you think's happening during 6 to 10? Well, I don't know what they want us to say exactly here, or what I want you to say. So skater moving in negative direction. Are they going backwards? Well, not necessarily. They could have turned around and be going like, facing forward, but going in the negative direction. Doesn't necessarily mean they're going backwards. They're just going in the negative direction. Determine the skater's average velocity from time 0 to 16. And just a reminder here, average velocity is displacement, final position minus initial position, divided by time elapsed. Okay, so final position minus initial, like symbolically, that's how we would write it. You've seen this before. And that's final position minus initial position over the amount of time gone by. So here, that average velocity is, what's the final position of the skater? You can look at your graph here, it's 8, or you can look here, it's 8. Minus, what's the initial position? 0. And those positions are in meters. And then how much time went by for the whole thing? 16 seconds. So that's 8 over 16. We like to do that, or even go ahead and write it as a decimal. So half a meter per second is the average velocity. Determine the skater's average speed. Now, average speed is the total distance traveled. So total distance over that same time elapsed. So I know that the, equals the time elapsed. That doesn't change. That's still 16 seconds. But what about the total distance traveled? So this, nothing can be negative when you're talking about total distance. If you go to Charlottesville and back and I say, what's your total distance? You're not going to tell me it was 0. You're going to tell me it was about 120 miles because you went there and then you came back. Total distance is always the sum of positive numbers. So here, let's just look at the graph and see what's going on. From here to here, going forward 4, and then staying still, so that's no distance, and then going backwards 2, but when we're counting total distance, we count everything as positive. So this is 4, and then 2 from here to here, and then from here to here is 6. So I've got 4, 2, and 6, right? Nothing happens here, nothing happens here. So 4 plus 2 plus 6 is 12 meters. All right. And that you can write either as a fraction or decimal. Either one is fine. I don't want you to write 3 meters over 4 seconds. You can do 3/4 of a meter every 1 second. In what situation might average speed be a better measure of motion than average velocity? Well, when would you want to know what your average speed was? If you were paying attention, for example, if you're driving around and you want to know what your, like how much gas you're going to use, then you don't care about the direction. It's not like when you drive back, like when you're driving back from Charlottesville, that you're somehow like getting your gas mileage back or something. You're still burning gas, so you want to know that total distance, and you would be more interested in your average speed. So in general, for average speed, it's really the differences when we care about total distance. And in what situation might average velocity be a measure of better measure of motion? Well, average velocity, if you only care about where something is at the end, like for example, if you needed to borrow my van to go pick up some drywall at Lowe's and drive it somewhere, and I said, sure, you can borrow my van. I'll leave the key on the front seat. It's in parking spot number 28 in the RCHS faculty parking lot. That is in fact, where my van is right now. So go ahead and borrow it and then bring it back, right? So for me, I don't care about like all the stuff like you drive to Lowe's and you get your drywall and then you bring it to wherever you need the drywall and you drop it off and then you bring the van back. So all I care about is at the end of the day when I go back out to the parking lot, guess where my van is? Right there, parking spot number 28. There's a light pole right there. You know where my parking spot is? It's the place where in the wintertime when it snows, they push all the snow up against this light pole, which is my parking spot. So that's kind of awesome. Big snowy parking spot. So here, in general, when we only care about final position. So all I care about is, I mean, did you decide to go through the McDonald's drive-through, get yourself a McCafe or something? I don't care as long as you're back in my parking spot, right? I only just care about this final position. So there's a couple examples of that. Other things you could say about those would be also correct, I think. All right, what's up with this? Rank the following. Rank the graphs according to which show the greatest average velocity from the beginning to the end of the motion. 0 is greater than negative, you knew that, and ties are possible. Okay, so this is average velocity. Now, average velocity only cares about, this is delta x over delta t. That's x final minus x initial over change in time. So I'm just going to find those. This only cares about where did you start and where did you end. What happened in between doesn't matter. So I'm just going to find those. Average velocity for A, B, C, D, E, and F. And then we can make our little list here, our ranking. So what's the average velocity for A? Well, this thing did not change its position. It stayed in the same place. So its change in position was 0 divided by 10 seconds. Here, this one also stayed in the same place. It wasn't the same location. This was at 25 and this was at 5. But its average velocity, it still ended at position 5 minus started at position 5. There's no change, so that's also 0. Just finding the slope of those, right? And then this one ended at position 10, started at position 0, so its delta x would be 10 over 10 seconds. So that's 1. In D, looks like we ended at the same place here, but it started at 3. So this x final minus x initial, that's 10 minus 3, it's 7 over 10. In E, I ended at position 0 and started at 15. So 0 minus 15, that's negative 15 over 10. All right, it's going in the negative direction. Makes sense that it would have a negative velocity. That's what that sign tells us, that it's going in the negative direction. And then how about this one? Well, this one, all I care about is its final position and its initial position. Its final position is 5, and its initial position is 0. So 5 minus 0 is 5 over 10. So that's 1/2, or 0.5. And I want you also to notice here that what we are effectively doing, it's like we're finding the slope of the line that connects the start to the end, and we don't care about what happens in between. That was rise 5 over 10. So this, I mean, that should look like a slope calculation to you. All right, so we want to put them from most positive to most negative. So the biggest positive is 1, or C rather. The number is 1. And then D, and then F, and then I got a tie here with A and B, so those could be either order, and then the only negative one was E. All right. Here, what about average speed? Now, speed can't be negative, and average speed is this the total distance divided by time. So those are going to change some of our answers, but I think some of them are not going to be different. So let's see. The things that are staying still, well, the average speed is still 0 because the total distance traveled is 0. So those didn't change. C, if something's going in the positive direction and it never turns around, that is not, then it's not going to have a different average speed and velocity, right? Because the total distance traveled and the x final minus x initial are the same. So that's the same. Total distance here is 10 divided by time, still 1. Same here. Total distance traveled is 7 meters over the time, so that's still that. Here, the total distance traveled is 15. Now, total distance, this cannot be negative. Distance can't be negative. Displacement can be negative, right, when we're doing this. But total distance, that's all the positive distance that you traveled, right? So that is 15 divided by 10. So this now, when we talk about speed, that's positive. And then this one is the most interesting because this went 10 and then 5, right? And if we're just tracking total distance, we're only adding up the positive stuff. So the total distance is 15 divided by 10 seconds. Gives me that. All right, ready to rank them. So from the greatest, we got a tie with E and F. That's a tie. And then C, D, and A and B tie with 0. That's it.